Okay, thank you everyone for joining. We'll just wait for a moment. Okay, so all the panelists are here, the moderators are here, so let's get started. Hey, thank you everyone for joining today. Welcome to the 8th virtual panel organized on behalf of CEDA CAD for Assurance Initiative. I am Professor Saurabh Vunia at University of Florida. I'm one of the members of this community, hardware security community, who took initiative several years ago during the peak of pandemic in October 2020 to create this CAD for Assurance initiative. It's basically an idea of creating a portal where we can collect the contributions from the research community in terms of tools, benchmarks, metrics, publications, methodologies, all those things into one platform. We call it CAD for Assurance, dedicated to help the research community in the broader hardware and system security and assurance area. That was the goal. With that goal in mind, several of us, of course, took a lead. Myself, Professor Gang Ku, Professor Sung-Yi Ho, and Professor Aydin are some of the members who took leadership in organizing this effort. But it was truly a community effort. And the entire community came forward and contributed to this effort to the point that we have actually 57 different CAD tools for assurance in the website right now, over 3,000 benchmarks. There are many other contributions you can find in the website. It's simple, cadforassurance.org. Feel free to visit that. We have more than 80 contributors from different parts of the globe, for more than 14,000 users, 44,000 page views from 126 countries. So it's really a significant effort driven by the community. And in parallel, we decided to use IEEE CEDA, particularly the Hardware Security Technical Committee, HSTTC, in CEDA, as a platform to organize webinars and panels and tool demos, as well as providing educational contents to students as well as researchers and practitioners in this area through different activities. And that's going on for last 3 years. We actually have more than 2,000 registrations in these panels, more than 1,500 attendees. Given the size of the hardware security community, I think it's a huge effort, and we're really pleased to have IEEE CEDA, HSTTC, and several industry sponsors for this effort. And in particular, I would like to acknowledge the industry sponsor, Mercury, HII, Northrop Grumman. Really appreciate their effort, as well as NAMES Institute at the University of Florida is one of the sponsors for this effort. One thing I would like to mention here is that being a community effort, we would solicit your contribution in any way you can provide contribution to the effort in terms of uploading your tools, benchmarks, publications, in terms of organizing webinars or panels. I would really appreciate if you can get involved. With that, I will go to today's panel. But before that, just to let you know that we had another panel a few months ago. That was the panel number 7 on microelectronic supply chain security. And if you have missed that, the recording for all these panels are available in the CEDA website, and I'll highly encourage you to go to the recording. Now, coming to today's panel, it's really an exciting topic, AI hardware security, very timely, very important topic. And I'm very pleased to tell you that we have a truly distinguished set of panelists in the panel. And then, of course, I will let the moderators to introduce. But my job here is to introduce the moderators. And we have really got two significant personalities or very prominent personalities from the hardware security area to lead the panel today as moderator. Professor Prabuddha Chakraborty from University of Maine and Professor Andrew, give me one moment. Sorry. I'm sorry. Yeah, Professor Andrew Lukefahr from Indiana University. They're significant contributors to the hardware security community. I would say rising stars or torch bearers for this community. They have contributed in many aspects of hardware and system security and assurance, including IP protection and hardware integrity protection. So with that, again, I'm pleased to have them as moderators. With that, I will hand over to Prabuddha and Andrew to take you from here, and thank you for joining.
Hey, thank you, Dr. Bunia. So yeah, me and Andrew will just take over from here. We will first introduce the panelists, and we would ask the panelists to provide a brief presentation in terms of their position with regard to this topic. You can present somewhere between 5 to 7 minutes. And after that, we would open the floor for questions, and we'll have a more open discussion, informal discussion about this topic. For the audience here, if you have any question at any time, please use the Q&A feature to put your question in there. It's better to use the Q&A feature rather than the comment, or rather the chat window, because it might get difficult to track questions in the chat. So just use the Q&A option. That is always easier to do. With that, just a little bit about AI hardware security and AI in general. Is right now AI is a $594 billion market in 2023, and IoT, which is also closely related to AI nowadays, also a $320 billion market. That was a 2022 figure. So all the major companies are in this domain. They are either building AI models or using AI models, or they're making AI hardware to accelerate AI models, right? And the three major reasons for having AI hardware is, you want to make the inferencing faster, you want to make the training faster, or you want to make the neural architecture search faster. Big companies, NVIDIA, AMD, Intel, AMD acquired Xilinx, Intel acquired Altera, Google is in the picture as well. So all these companies are working towards making AI hardware more efficient. But the question today is, how secure are they? And what are the security concerns that might be there that might impact mission critical applications? So with that, I will hand over to Andrew, who will introduce our first panelist, Chris Taylor.
All right, so Chris Taylor is up first. He is an experienced professional in integrated circuit design and hardware security. His academic credentials include bachelor's and master's in electrical engineering from Wright State, followed by a master's and PhD from the Ohio State University. For the past decade, he's leveraged his expertise, making significant strides in making hardware systems more secure, developing methodologies to measure and prove their assurance. In Dr. Taylor's current role as a senior research scientist at Battelle, he has been developing frameworks for composable system-level risk models to forecast potential vulnerabilities, security risks, enabling preemptive measures and solutions, as well as cost optimizations. So with that, we'll turn it over to Chris.
All right. Let me go ahead and share my screen. I just have one slide today. I will say the Ohio State University, the is legally required, so I do appreciate you including that.
I'm a Michigan grad, so those two schools compete quite a bit.
Yeah, so I'm gonna maybe, especially how I'm looking at it in my current role, because I'm really looking at a systems perspective. And when I think about AI, I always want to think about the implications and what I can communicate to somebody who is integrating a platform, and not necessarily where it sits or how it affects a singular chip or piece of hardware. So I modeled this slide after the good, the bad, and the ugly movie, because there's good things about AI for hardware security. There's very bad things, and then there's just kind of this ugly area for AI in general. So for good, I mean, there's a lot of things that we can use AI and ML algorithms for that have been really great, and they have been definitely maturing over the last probably decades at this point. But things like doing runtime anomaly detection, issues with your chip, things people have been doing to make sure that they're not operating how it shouldn't be intended. We've seen a lot of Trojan detection algorithms. I think almost universally, AI ML for Trojan detection is pretty much the way to go. Doing firmware analysis. Excuse me. Test article generation. We never have enough test articles in hardware. That's really, really hard because there's just not as much open source. So generating test articles with AI algorithms has definitely been the way to go there. With the LLMs becoming very, very popular with ChatGPT in the last year or so, unstructured data analysis. If new vulnerabilities pop up, if new academic papers come out, looking at and being able to analyze those papers, not manually, but using those LLMs has been really great, at least for especially for the stuff that I do at Battelle. Optimization, we're starting to see the CAD tools build in ML into the optimization algorithms. And then supply chain analysis. We saw that over COVID. We saw the lack of resources or availability of chips. And then we've also even seen the DoD has been really pushing a lot more analysis into the supply chain of the chips and components and designs that go into our systems. Now, with all the good, we can flip everything, and every single one of those things can become a bad thing for us. Secret key recovery. So a lot of the logic redaction, logic obfuscation, ML algorithms for recovering those keys and making those techniques moot. Side channel analysis. It gets a lot better using AI ML, and it becomes a lot harder to protect. Fault injection analysis. Okay, now we can protect from faults, but now it's easier to insert them using ML. Trojan insertion, so great for detection, also great for inserting Trojans. I think one of the biggest hurdles for actually Trojan insertion is the difficulty in understanding the design you're inserting something into and putting something in that actually will give you a useful output that you can then trigger later. So really what happens is the window of opportunity is it's smaller than how long it would actually take for a person to do this. Now, AI, ML, it makes it easier, it makes it quicker. And so those windows of opportunity, they have to be smaller. So this becomes a lot more difficult to protect against. Reverse engineering, while it could be a good thing if you're trying to protect your own designs, it's a bad thing if you're trying to protect your IP. And then supply chain analysis. We do the same thing to understand our supply chains, how we can be resilient. Somebody else can do it to understand how to attack us, where our critical points are, how they can disrupt our availability to state-of-the-art devices. And then the ugly part of AI ML is the attack model now changes. Now we're adding in these new algorithms that they're harder to explain, they're harder to test, and so adversaries can poison the data that we're using. They can just poison the models themselves, so they can evade them using evasive attacks. And the problem is it's harder to test corner cases in AI ML versus traditional software. So it's harder to understand how somebody's going to get around the algorithm because it's harder for us to actually test weird cases that might be presented. And we see that a lot with LLMs as people try to get around the protection with them, like for ChatGPT. And if you input like a random string of characters, it is confused and then it answers questions that it's not supposed to. Model inversion attacks, we're putting a lot into these models. You can leak information out of them. Inserting backdoors into the models, similar to the Trojan attacks, but now the models themselves are susceptible, and it's harder to test for these or understand how they could be placed in. Depending on how your algorithm is deployed, especially if you're using like a service, just exhausting your resources. These are pretty computationally intensive, so this is it's not too difficult to do some sort of DDoS attack on them. And then I think one that's a little bit more unique to hardware is the lack of data sets. I think the thing that we at Battelle struggle with the most when we're doing anything hardware related in AI is we never have enough data sets. There's not enough open source data, and IP for hardware is expensive and it's proprietary, and it's just hard to get enough information to actually generate really good models, which makes data poisoning attacks easier, model poisoning attacks easier because we just don't have enough data to be able to test everything. And with that, I will pass it back to the moderators.
Thank you, Chris. Thank you so much. So we will move on to the next panelist. We'll introduce everyone, then we'll kind of come back and discuss all these points. These are really interesting things you mentioned. So our next panelist is Hubertus Franke. So Dr. Franke is a distinguished research staff member at the IBM T.J. Watson Research Center since 1993. Dr. Franke graduated with a diploma in informatics degree, MS Computer Science from the University of Karlsruhe, now KIT, Germany, in 1987. He obtained a PhD in electrical engineering in 1992 from Vanderbilt University. He leads projects in high-performance computing, computer architecture and accelerator design, operating system, cloud systems, software engineering, compilers, and robotics. He co-authored 142 publications in peer-reviewed conferences and journals. He holds 178 patents. He's an ACM Fellow and IBM Master Innovator and member of the IBM Academy of Technology. He has been an adjunct full professor at the Courant Institute at New York University, year-round teaching graduate classes in the field of operating systems since 2011, and an adjunct research professor at ECE, University of Illinois Urbana-Champaign since 2022. So that's a fantastic career. So, I'll pass it over to Dr. Franke.
How you doing? Okay, so I'm too many fields here right now, so I'm just going to present this way, getting all the controls out of the way. Let me see where I can get it. Here it is. Okay, so thanks for the introduction. My area currently, where I'm looking at is some of the areas actually in confidential computing, and we're looking at accelerated machine learning. So let me just go into the confidential computing and machine learning. Really, if you're looking at confidential computing, it's really regulated environments are driving new requirements, and particular healthcare, financial governments, they're basically imposing certain constraints on how data effectively have to be handled. And that basically constitutes how system architecture have been evolving, right? And this whole field of confidential computing over the last, I would say, 3 years has really becoming very visible by various providers, cloud providers and so on, right? At the end of the day, if you're looking at the regulated environments, you really want to achieve this, what we call confidentiality, integrity, and security compliance. Confidentiality effectively means nobody can look at your data, and we all can hopefully relate to that when we're thinking about our own financial statements and our health records, right? We want to make sure that nobody can modify those, right? And then at the end of the day, there are compliance issues. That means I can actually validate that these characteristics are essentially obtained. Now, confidential computing basically zooms down on 3 parts, right? This protect your data at rest when it's in storage, protect while it's in motion, and then finally in compute. While the first 2 are well known, right? We have deployed them for decades, right? In compute is effectively now being facilitated by advances that we can see coming in pretty much every computer architecture out there, right? It's largely relates on using encryption technologies. We're also now interested, as we're basically going into these new fields, it's not just about a single VM or a single instance anymore. You need to essentially make sure that you can scale up as we're pushing these technologies out into the cloud. And you have to basically achieve high performance. There's very little price you want to pay, right? I mean, it's like in insurance, right? The moment the insurance goes up, you basically effectively make a judgment whether you want to pay for it. Finally, as we are driving into cloud environment, you also have to think about multi-cloud environments, right? Maybe you want to take something from Amazon, maybe you want to take something from Azure, right? Ultimately, confidential computing's vision is to move from a trust model where I trust the provider, particularly the cloud provider, to a technical assurance where I can verify that actually the technology confines with confidential computing. Now, going to the topic of this panel here, we're moving to how we're integrating with machine learning, right? Again, the discussions are around this topic are that machine learning models by themselves, and particularly also the input data that I'm using to either do an inference or basically to do a subsequence fine-tuning of the machine model by themselves are seen as assets, and they need to be protected, okay? So I want to basically deploy them in the cloud. So I have to anticipate in many cases that there might be a multi-tenancy issue. And the moment you have multi-tenancy issue, as Chris was saying before, you have to be concerned about side channel attacks and so on and so forth, right? Now, in machine learning itself, or in AI, right, hardware acceleration is basically the standard now. You have to have it. There are very few scenarios where you can get away with just doing things at the CPU level, right? And so there are many different accelerators out there. You know, GPU is probably the most dominant one, TPU from Google and so on, other ones, AIUs, what we have in IBM. But FPGAs, everything is basically becoming an acceleration unit that you have to integrate with. So as confidential computing largely is basically delivered what we call it a trusted execution environment, a TEE, that manifests itself typically as a virtual machine running on either Intel or AMD hardware, you know, maybe on proprietary hardware. Now we must integrate CPUs, these CPUs with accelerators, right? Now these accelerators don't necessarily need to have encryption. It's desirable, but you can also have very strong isolation to achieve that. So I wanted to give one example here, right? So most of you are familiar with the NVIDIA, and to me, that's currently the gold standard for a device that provides me confidential computing. And if you look at their websites, you know, the way they advertise it is you have a GPU. Hopefully you can see my cursor. You have a GPU. The GPU itself can be partitioned, and they are very strong partitions. That means you cannot break through these from one partition to the next one. And then you allocate these virtual machines as trusted execution environment that use encrypted memory behind it, right? So that even if you have a hypervisor escape, the hypervisor cannot modify or cannot read the data, right? It's all junk to it, okay? Then we have basically using device drivers to run communication across to the VM. So technically speaking, as we're discussing our machine learning kind of application, we're looking at this blue box as a single entity and calling it a trusted execution environment. However, the reality is completely different, right? We really cannot treat this as a single TEE. You actually have to look at it as a complex of different TEEs, and each of them have to have their own encryption keys. They cannot be shared, right? You don't want that. You don't even want to strive to that. The next thing is basically you have to attest that the device you're communicating with is actually a device that you know about. It's not basically a fake device, right? Data on each of these TEEs, right, and I call it our GPU is a sub-TEE, right, needs to be protected, right? So we need to either encrypt or isolate. Every communication, I've drawn here every possible communication you can think about, right, in red and blue and green or whatever these colors are, needs to be protected, and they need to be protected via ephemeral keys, okay? This also then requires us to have additional hardware that go deep down into our computer architectures, right? So for instance, IOMU is the ability for a device to do a DMA into your host memory. Well, if you have a device that you can't trust and that basically grabs memory from your host, you effectively have leaks, right? And then finally, you have to have a full lifecycle management for trusted execution environment. So how do I make sure that once I linger one of these partitions here on the left side, right, that these the lifecycle basically means that the memory is scrapped and it needs to be all verifiable. Otherwise, I can't have trust. That finally drives me to standards, right? In this area, there's always what you see in any kind of advancement, people kind of jockeying ahead, right, and basically implementing a solution. But people start thinking about it and they're evolving these standards. And the current standards that we really need to look at is, for instance, I listed 4 of them, like the SPDM, which is a protocol and a data model, how we actually setting up encrypted channels between between end devices, right? A TDIS, which is basically what a device needs to provide in order to be considered trustworthy, right? We need data encryption, which is now part of the standard in PCI, and we need the device standard for the TEIO. So my encouragement is really looking at standards like this for anybody who's ultimately implementing an accelerator has to at least coerce to most of these issues, and that's kind of the area where I'm currently working in. Thanks.
All right, thank you, Hubertus. Our next speaker is Aysu. Aydin is a assistant professor and Burnett Faculty Fellow at the Electrical and Computer Engineering Department of North Carolina State University, where he leads the Hardware Security Research Lab. He has his master's from Sabakçı University in Turkey and his PhD from Virginia Tech. Before joining NC State, he was a postdoctoral researcher at the University of Texas at Austin. His research are broadly in hardware security and cybersecurity education. His hardware security research has won NSF Career, NSF CRII, Google's RSP, and Goodnight Innovation Fellowship Awards. He's got 6 Best Paper nominees, 2 Best Paper Awards, 1 hardware security top picks, and 1 publicity paper award. He's also the co-founder of Nithril AI Corp, a startup working on secure AI chiplets. Did I get the name Nithril correct?
Yeah, that's great. Thank you for your introduction, and thank you for inviting me to this distinguished panel. So let me go ahead and share my screen. Right. Are you able to see my slides?
Yep.
Yes.
All right. My pointer as well. All right. Thanks again for having me. So I do have 2 hats, one as a professor and one as a recent entrepreneur. But for the scope of this panel, I'll stick mostly to my academic hat. So I will first describe what we do in general sense, and then I would like to highlight one particular problem that really gets me exciting about AI hardware security. So it's easier to describe what we do not do. The typical cybersecurity image that comes to people's mind, which is typically a college dropout with a hoodie typing code into a terminal real fast to hack a system remotely. So this is not what we do. Instead, the kind of research we do is actually highlighted with this slide. This is from our recent paper published at DAC, where we showed a physical side channel attack that can steal AES keys from an iPhone. And we have achieved that by first taking the backside of the iPhone, cutting out power cords and feeding us our own clean power into the system. And then by reverse engineering the schematic to find secret test pins into the PCB that can directly issue commands into the hardware where the crypto is running. And then we use an electromagnetic side channel attack. We capture electromagnetic signals and then use some advanced AI techniques and classical statistical techniques to figure out the secret keys. And here is just another example, the same example zoomed in, where we first look at the high activity regions by scanning the chip with a highly capable electromagnetic probe, and then use these signals to figure out the secret keys. More broadly, my work has 2 focus, which is a great which is really suitable for this panel. So I work on hardware security for AI and AI for hardware security. So the first thrust, which is on secure implementation for emerging crypto, is actually about building custom accelerated units and architectural support for these emerging crypto that includes homomorphic encryption, for example, and post-quantum crypto. And there I do see a lot of efforts, including ours, that can use AI to, for example, counter side channel attacks and fault injection attacks, among other things. The second thrust is on secure implementations for AI. So this is really hardware security for AI. And there, I think the key challenge is to apply the techniques we learned from crypto, right? So there is over 2 decades of research on how to make cryptographic circuits more secure. And now these attacks, these hardware attacks, are emerging for AI/ML systems. These attacks include things like side channel attacks, fault injection attacks, cold boot attacks, access control violation attacks, probing attacks, and so on and so forth, and also hardware trojans as well. So how can we leverage the techniques we have developed in crypto and apply them to AI/ML hardware is another thing that I really am excited for. The third thrust is on how to do these analysis before we tape out the chip, because it's too late if you make a mistake after we tape out the chip. and how do we do pre-silicon analysis using AI to counter these hardware attacks is also very important. And of course, there is also the problem that has been mentioned before on supply chain and untrusted foundries. So these foundries do not only create crypto chips, they now also make AI chips or AI or PCBs that contain AI units. So how do we handle that is also unknown. And finally, raising the workforce, which is barely discussed. There are a lot of jobs available. There is a well-known cybersecurity talent gap. And this gap is even harder to fill for hardware cybersecurity specialists. And I also work on how to do this with better tools and with open source ecosystem designs. And finally, I would like to leave with this slide. So, and I would like to emphasize one problem that is really exciting. We know that side channel and fault injection attacks are valid for crypto, and there are multiple companies and startups that work on protect crypto chips against these attacks. And I would argue that these attacks are now emerging for AI/ML designs and AI/ML hardware. You can steal valuable trained IPs, trained models using side channel attacks, and you can cause critical misclassification through fault injection attacks. So we need better solutions that enforce security at the hardware, because without trusted silicon, we cannot achieve trusted AI/ML systems. And in my lab, we have taped out a chip that can actually achieve this for the first time through the use of what we call masking and shuffling techniques, essentially by randomizing solutions in randomizing computations in hardware to counter these kinds of attacks. And we have taped out this using 130 nanometer Skywater fab. And this work is currently being transitioned to practice by the company that I co-founded. And thanks very much for your time, and I look forward to having an engaging session today.
Thank you, Aydin. We'll move on to the next panelist, and we'll come back to all these interesting topics that we discussed. So all of these are worth discussing more. So our next panelist is Dr. Wayne Churaman. I hope I pronounced that correctly. So Dr. Wayne received his PS and MS in electrical engineering, his PhD in mechanical engineering from the University of Maryland College Park. He served as the team lead for Protective Technologies team within the Electromagnetic Spectrum Science Division at DEFCOM Army Research Laboratory from 2018 till 2023, where he oversaw numerous classified programs in secure packaging and novel security solutions for microelectronics. Dr. Churaman currently serves on both the Technical Planning Committee and the Steering Committee for the Government Microcircuit Applications and Circuit Critical Technology (COMACTEC) conference, and is now serving as the Secure Edge IoT Computing Technical Executive Area Lead under the DoD's Microelectronic Commons. So Dr. Wayne, would you like to introduce yourself more and talk a little bit about your research and what you're doing?
Great, thanks for the introduction. Can you actually see the slide that says Microelectronics Commons? Is it coming through?
I can also see myself as well.
Oh, you can see yourself. Okay, how about now?
Just double click to make that big.
Okay, is that coming?
Yes.
Yeah, there we go.
Okay. All right. Yeah. So thank you guys for the opportunity. I'm gonna probably talk about this at a very high level, but so my background is based in sort of looking at anti-tamper and hardware security, not necessarily related to AI, but I think there's definitely a lot of direct connections between AI and hardware security itself. I guess I'll talk about this from my new role within the Microelectronics Commons. And so the Commons was set up under President Biden's CHIPS Act. And, you know, as part of that, there has been the establishment of 8 regional hubs. And these hubs are meant to align with 6 of the technical application areas. So I'm going to be overseeing the secure edge IoT compute. But there are other areas, including 5G, 6G, and of course, AI hardware, quantum, electronic warfare, and commercial leap ahead. So I think within my technical area, with regards to the secure edge, we're looking at how do we protect forward deployed systems that are operating beyond our control, right? So things that may potentially be left behind, things that are computing at high levels and providing data and information to the warfighter. The biggest concern that we have is that as we push state-of-the-art pieces of hardware to the edge, they're going to potentially be left, and there's opportunities for those things to be compromised. So while I will be managing a portfolio in the secure edge space, I'm hoping that through engagements like this, the conversations that we're having this morning, that we'll start looking at how to address security questions related to AI. How do we use AI to make sure that our IoT devices are giving us the information that we need when we're operating in adversary territories and places that we don't necessarily have control over our environment. The overall mission of the Microelectronic Commons is really to go from lab to fab, prototyping capability, and being able to work with core facilities that are domestic based entities to provide these manufacturing capabilities so that we're not necessarily reliant on foreign entities. And really, this graph kind of summarizes our mission and our goal. I think, with Microelectronic Commons, we're farther to the left. We're looking at engaging with the research institutes who are leading up these technical areas, but also we're looking at opportunities to engage these researchers with DoD priorities and with DoD labs so that we can ensure that the prototypes and the solutions that are coming out of the research space end up making it across the transition valley of death so that we can get direct engagement and buy-in from the defense industrial base and from the commercial side. Because I think having partnerships with commercial entities is going to ensure that the technologies that we leverage in the future make it onto the battlefield and make it into the hands of the warfighter. So really, I'm glad to be part of this conversation. I'm hoping that maybe we can have some additional side conversation about how some of these technologies and questions can be answered within the confines and the constructs of the ME Commons as we're looking to build out secure edge and IoT over the next 5 years, and looking at the different type of investments, because I think there's going to be direct overlap between AI hardware and the secure edge compute. So my hope is that you all, if you're not part of one of these existing hubs, that you'll think about becoming a member, and you'll think about how do we connect some of these bubbles here, right? Because I don't think that they're necessarily independent. I think there's a lot of interconnectivity between each one of these technical execution areas. So with that, I really do thank you for allowing me to share this morning.
Thank you so much, Wayne. That's a fantastic presentation. And yes, ME Commons is a great effort going on over there. Andrew, you want to introduce our final?
Yeah, so last but definitely not least, I want to introduce Chris Sozio. Chris graduated from Indiana University in 2019. After that, he went on to be a scientist at the Naval Surface Warfare Center Crane, or NSWC-Crane, where he supports the Trusted and Assured Microelectronics, which is also known as TNAM, FPGA assurance efforts regarding FPGA security research and verification and validation for performer development tools of FPGA assurance. He has 1 patent pending and has authored or co-authored 3 conference publications. Chris, take it away.
Yep. Thank you, Andrew, for that introduction. So first, I just wanted to say thank you for CAD for Assurance for inviting me to be a part of this panel, and I'm looking forward to adding my experience to this topic at hand today. And I also want to just state that these opinions are my opinions and not of those of the United States government. So with the intro of ChatGPT and DALL-E and some of these other AI technologies, we saw this kind of massive wave of interest for this technology from the entire world, not just hardware security and not just technology positions, but also from general populace. We also had all these multiple companies join in on this hype train, almost essentially, and hire a bunch of AI technicians or engineers in order to start developing their products and their tools. And luckily, this interest brings in a lot of eyeballs on this topic of AI development in order to hopefully increase the hardware performance and optimization of these architectures. But as always, as I've seen in the past, security is more of a secondhand thought or kind of existing off to the side, right? This is never really brought up into the forefront of the designers' minds or really the business side of things. And this could be extremely critical to ensuring that these systems are actually protected. So hopefully today we can talk more about that and get into how we might be able to start convincing some of these designers that security is a big topic. And to kind of jump into one of the questions that was on the panel introduction slide but is the state-of-the-art hardware architectures secure or not? And I think the immediate answer is, for now they are secure, but will they eventually still be secure in the next 5, 10, 15 years? As kind of more in my area of expertise of hardware security or FPGA security, we look at the Starbleed attack, which was published here recently within the last 3 years, and then again for a later generation last year. These attacks on Xilinx FPGAs were not known until many, many, many years after production and deployment of these systems, right? So we initially thought that these systems were going to be secure. We could use them in our applications and be trustworthy of those devices. But really, this is not necessarily the case. And time to time again, we see the actual hardware being affected or attacked. So this Starbleed attack, if you're not aware of it, actually enables the adversaries or bad actors to extract the bitstream from the FPGA without affecting the actual device, as well as allow them to reverse engineer the bitstream that they get pulled off through plaintext, which can then be altered, re-encrypted, and reprogrammed back into the FPGA. And for this topic, potentially altering your AI applications, either for good or for bad, mainly. We also see the effect of multi-tenancy FPGAs in the cloud running potential applications being affected by potentially other users that are within that same FPGA. Again, this could affect potential AI applications quite effectively, which have been talked about in papers and will probably be continued to talk about. And looking at edge systems, mainly existing out in the field, right, where they might not necessarily be constantly communicating with a remote server or a central server. So we need to be able to identify or authenticate that these edge systems have not been tampered with, are correctly sending in over the appropriate data, and nothing has affected these devices. So kind of alongside that, AI can be used in unfortunately bad, and what has been talked about previously by the other panelists, bad actor way, where we could potentially automate the effects of side channel analysis, determination of vulnerabilities. So fuzzing bit streams is kind of a thing that I've been looking into, trying to determine the configuration and see if there's any potential negative effects of changing that configuration within the bit stream. But also it can also be used in a good manner for example, anomaly detection, just general security analysis regarding code coverage, test generations and optimizations, potentially predictive maintenance, which is kind of a big topic for Navy. With the ships being out in the field, we want to be able to identify that these systems might be degrading, and how can we effectively fix those at a quick and responsive time. AI is also able to help generate interesting configurations of these devices, which might not be potentially thought about through our brains, potentially giving us an insight into how to protect these systems better. And really, this technology, with its hype train kind of coming around here within the last couple of years, is really going to offer us many opportunities and areas to continue to explore into. And really, put simply, AI is a double-edged sword, and we're really going to have to be able to leverage it on the good side of things and prevent the bad side of it. And I also just really want to reiterate what Aydin talked about previously on the workforce development. That, to me, is a big, strong point and an interest of mine in mentoring these younger engineers, making sure that they are aware of all these different technologies and helping them through their careers, I think will be a massive help. And I employ a lot of you to go help with that. And to kind of shamelessly talk about the Navy and potentially Navy systems. So we want to be able to utilize heavily AI and ML within these unmanned systems regarding around unmanned undersea vehicles, so UUVs, unmanned surface vehicles, USVs, and then autonomous drones, right? These systems are going to be extremely advanced and are going to require the use of a lot of AI and ML applications in order to help out with navigations, communications, deterrence, and intelligence. And more specifically around the intelligence, right? These systems might be going into a stealth mission, and so they're going to go offline and not communicate with our central systems for a long period of time. When they do come back online, we want to make sure that these are properly vetted and that nothing has been messing with these systems and potentially changing their configuration. So all in all, this is going to be a very interesting field for us in the future, and really just for the rest of our lives. Is this, I do see AI being there forever. So with that, I thank you all, and I guess we can get into the Q&A.
Thanks, Chris. Everyone is really excited about your presentation. They have been asking, why do we not see any slides? So unfortunately, everyone, there's some compliance reasons we couldn't share the slides, right, Chris? But
yeah, so I was not able to get it through the public affairs in time, so I apologize to everybody.
But yeah, but we have a lot of great questions that have been asked, and I would like everyone in the attendance, please ask your questions, whatever you have in your mind regarding AI hardware security. It's a very big field. It's an emerging field. It's a ever-widening field. And I've taken notes of from all the speakers. I have some questions for you, but first, I think we should take the questions from the audience first. So I see a couple of questions here regarding GPT and how GPT can, or generative AI in general, I guess, can impact hardware security or AI hardware security. Because since ChatGPT, since last November, everyone is only talking about ChatGPT. So I think maybe we should take that question first and see how GPT might impact positively or negatively different aspects of hardware security and AI hardware security. Feel free to jump in. So now it's open. Yeah.
Let me take a step at it, right? So
sure.
First of all, there's not just ChatGPT, right? I mean, you will actually in the industry go out and say, hey, there's one big model for everything, and there are different opinions that effectively say you need actually more fine-tuned model to get higher accuracy and things like this. The moment you start fine-tuning it, right, you will have to have your own data in there, and that essentially will require you to release some of those data for the machine learning or for the fine-tuning purpose, right? And in my opinion, that will actually drive more and more security. In essence, if you're starting out with a foundational model that ultimately can be shared, many of those are out there like Llama and so on, right? And you would like to do a fine tuning of that. You want to have the llama, which everybody can agree of, as long as it's being signed and things like this, you can attest that it's actually the original llama model that you're starting out with. That can be shared, but for all your other things that you're basically injecting into the learning process now that's potentially running in open systems, you definitely want to have confidentiality and integrity, right? So I firmly believe there will be changes to hardware that we have to drive where we effectively can have a duality of open information coupled with closed information, right? And that essentially again needs to be pushed down at the hardware level.
Great, thanks. Would anyone else would like to
Yeah,
chat?
I'll just chime in just for a bit. Yeah, I mean, one thing I mentioned earlier in my slides was lack of data, lack of test models, or just lack of hardware examples. And so generative AI or GPT, I mean, it's really good at generating, maybe not the best examples in the world, but generating a lot of them in quickly. And I think the biggest issue that we have a lot not only is we don't have those examples, but we also have a lack of subject matter expertise to even do a lot of this analysis, do a lot of this generation. So we almost see those types of tools to be, almost a force multiplier effect where, we can be more efficient, we can quickly do things, generate more designs, generate more examples, insert more modifications or whatever we're trying to test. So it helps us do that. It makes us more efficient and more effective. I mean, I can't tell you how much we actually use ChatGPT just in our day-to-day work now, just because of how useful it is and how much it's made our lives quicker. And I think, yeah, with that, I'll pass it back.
Do you see, GPT models being used to come up with novel vulnerabilities or create new attack surface due to the generative nature? Is that, think of from that angle, is that possible?
I would say maybe possible, maybe not completely realistic. I guess, I don't think ChatGPT could, but maybe if you have your own, but it could come with variations of ones that already exist, which, that helps, itself immensely. It's just variations around it because it might catch some edge cases or some corner cases that you weren't thinking of. And that's where we find the most use there. But, if your SMEs are coming up with the novel type attacks in your ChatGPTs or your, there's hardware specific ones now, but your generative AI is generating all the variations around those. Well, you can have your one designer generate thousands of different test articles that otherwise would just not be possible. And just the value of that data is immense.
Right. Thanks, Chris. Aydin, you want to pitch in? I know you have worked a lot with this kind of things.
Yeah, first of all, just plug in my academic mind. So there is a paper published by University of Florida, like our colleagues there, that evaluates how all these different kind of hardware attacks from Trojans to side channels can be either mitigated or extended using ChatGPT and other large language models in general. I think there will be an impact on how to create better specs or more accurate specs. That is one definite improvement that I can see. But I think there is a very serious risk of creating vulnerabilities or vulnerable code using ChatGPT. And doing it automatically is I think very dangerous. Even the GPT itself can be jailbroken and can be tampered with to create some vulnerable code. For example, like a vulnerable multiplier code that adds with an extra AND gate that can only corrupt with certain properties. So yeah, I mean, but I don't know how it will pan out in the end. So it's very new and very exciting for sure.
Yeah, so I would like to jump in there, and I completely agree with Aydin on that aspect of ChatGPT or any of these GPT models could be used effectively to introduce potentially hardware vulnerabilities, but also just by inexperienced engineers using them and not necessarily understanding what they're looking at or what they need to be able to how to prompt the system to properly give back a solution that they're looking for. and just incorporating that piece of code maybe into their RTL could potentially introduce bugs or hidden features that the overall design is not necessarily aware of. So I think GPT, again, is kind of also a double-edged sword where it can be used beneficially or it can be used in a bad actor way or maliciously.
Thanks, Chris. Wayne, you want to add anything to that? Your thoughts?
No, I think these guys summarize it pretty well. I know from a laboratory perspective, we've seen, utilization of ChatGPT to create a lot of code for our testing routines. But I think from a security point of view, we do have to be concerned about how much we open ourselves to, outside players, right? So we really have to think about where the information is coming from and how we're using it, especially in a lot of our DoD systems.
Thanks, Wayne. Andrew, you want to moderate the next
Yeah,
question?
so the next one I got here is on chiplets. So imagine a system where you're trying to do a secure AI processor and you get stuck on a interposer with another chiplet that's trying to attack you. How do you counter that? How do you defend against kind of adversarial chiplets that somehow ended up on the same system as you?
I'll just start. I don't know if this is too much different than the third-party IP problem that we have now. Just the integration is a little bit different. Now the integration is, you're going to probably have a lot more variation in the sources of that. As in, there's only so many third-party IP vendors that you're going to purchase from, especially since you're limited on who has what you need in that specific technology. And chiplets will enable that to be much broader, probably a lot more marketplaces than where you're getting third-party IP, and maybe a lot more less great suppliers that might be selling cheaper IP. So I think the attack surface is going to expand because your supply chain into those chips is also going to expand. So I don't think the attacks are too much different. Maybe the integration is a little bit different between on-chip versus chiplets. But your attack surface from where you're getting the devices is going to be a lot bigger and a lot harder to protect against. So I think, as the DoD is already looking at this third-party IP, when they were doing the RAMP program, when they were looking at microelectronics quantifiable assurance, that was like the biggest concern and the hardest thing to protect against. And chiplets is just going to make that way harder and a lot more of a concern to look at, because now there's just going to be a lot more variation in that space. I don't know if I actually answered the question. I'm just talking over how I'm very concerned about it, and I think we're gonna have to take a lot more protections when we start to do those integrations.
So let me also comment on this. I believe the fundamental principle that I showed earlier on, where you essentially have to do an attestation of the components that are in your system, whether they are devices attached to a bus or something, will effectively play in the same way as you're basically going to chiplets, right? I mean, I can send out a design and saying, okay, a bunch of wires, I essentially connect one of the devices, but I have to, at any given time, also ascertain. So we're moving probably away from a single root of trust that we have on the device to something where every chiplet has to have at least a very rudimentary root of trust. That means a device has a verifiable signature on it, right? It can be attested against it, and potentially can be measured with, right? So, for instance, if I'm a device or a chiplet manufacturer, I could put certain PUF technology into my chiplet, right? And that can be exercised and can be verified, right? And so all you basically observe as a client of that chiplet would be a certain signature and a certain behavior when triggered in a certain way, right? And I think that's where we're heading.
So you're suggesting that every chip needs to have
every chiplet
ability to authenticate itself against
every chiplet, yes.
Yeah, every chiplet. Okay.
Yeah, if I can jump in, I think this is going to open up some unique concepts in sort of advanced packaging, right? As we move to chiplet integration and sort of looking at 3D and 2.5D heterogeneous integration. So I think the advanced packaging is going to look at, how do we minimize leakage and crosstalk, especially as what are the methods of extraction, right, that an AI might use to pull the information off. So I think that's something that we kind of gloss over is how are we going to package these things too, right? Looking at the broadening threat space that's out there. Sorry.
Yeah, Aydin, Chris, Sozio, you guys want to add anything?
Yeah, sure. So I agree a lot with what Hubertus said, that, and it almost kind of brings up the zero trust model for a lot of these chiplets. Is you're going to have to work on vetting the individual chiplets through either a PUF infrastructure or some message authentication code or some capability in order to actually begin or before you begin to trust that these chiplets are going to be providing you with appropriate information and not going to be adversarial towards you.
Right, Aydin?
Yeah, I
Anything
agree. Someone needs to convince everyone that we need to have these things, and somebody should pay the costs, right? So I'm not sure if everyone will be excited about putting more overhead into their chiplets. And that's, I think we should really work together and push this idea so that people are convinced of the overheads.
So there's a challenge there with, I mean, a lot of these chiplets are going to be mostly commercial, and we run into this with FPGAs. Like, they don't want to add security features because they take up die space. So,
yeah, but you have a lot of dark silicon these days on the chip, right? It's always easy to sell insurance after the tornado hit. It's always hard to do it before, right?
Yeah, that brings us to the next question. And one of the attendees, Payman, has asked, considering the rapid evolution of AI technologies, how does the life cycle management of AI hardware system impact the long-term security? So essentially, it's bringing in the fact that we do not have enough time to design these things. We have a very short time to design and put it out in the market. So is the security aspect the first feature that gets the axe? And because we cannot compromise the performance, so is it that security gets left behind, and how do we address this problem?
So how do we address it is a good question. Security is absolutely usually the thing that gets tacked on at the very end, right? It does create additional overhead in terms of real estate and power. And usually programs, unless they are forced to apply security measures, whether that's volume protection or encryption or PUF, whatever that is, it generally comes as an afterthought. So I think we do need to think carefully about how do we bring security into the forefront. The timescales, that's a big challenge, right? Because security does require additional time and resources to come up with the solutions. So no, that's a very good question.
I think some security is better than no security, right? So the deeper you actually dwell in, and we see this effectively on CPU technology, which has probably a runway of about 8 years to look at this, and you see about 4 or 5 generations of stronger and stronger CPU security being deployed, right? The effort that needs to be dispersed in order to basically find new side channel attacks or new attack ways on these hardwares is becoming exponentially larger. Well, we can argue about the exponential, right? So to me, you make security a first principle, first design principle, right? Just for instance, saying that chiplets will have to have this kind of technology in. And if you don't want it in a particular version because it's too expensive, or you have a clientele that just simply doesn't want to deploy it and pay the overhead for it, you chicken switch it out, right? You just don't power it internally. Right? I mean, these techniques are available, but I stipulate at the end of the day when, I mean, take example like recently the solar flare where they actually got in large trouble with the government, right? The big equalizer is always money, right? If you convert it into money, into fines, into something of that nature, right? Then people are listening, right? And they will put certain technologies in.
Yeah, and that kind of brings us to what Chris Sozio was presenting. He mentioned that we need to bring security from the very first. When we're designing it, we should consider the security aspect. So, what are your thoughts on this? Will bringing in security during the initial design phase make the life cycle longer? Is it still feasible for us? And how can we kind of fit it in there? And how can we convince the stakeholders to consider security?
Yeah, so I mean, I think it plays along with some of what we look into at the Crane side and Navy side, really, is some of our programs are going to need to exist for 10, 20, 30 years, right? We need to be able to reliably be confident upon these systems to work. So we need to also be able to ensure that they're going to be secure. And I think that's, again, I agree with what was previously said of it's going to be a tall task of trying to play the number games and essentially the money of trying to convince the stakeholders that the security is a big problem and needs to be a part of the initial design process. It's again, it's going to be a tall task that we're going to have to constantly fight, but I think it can be done as long as we kind of start to talk more in lines with the business side of things and ensure that they're aware of what the stakes are with security.
I think just to add my 2 cents, because I know we're talking about, putting security on the forefront during the design, and then also trying to understand the cost implications, and then also not only put the security in, but if you don't have proper security, what's the cost implication to the company, whether they get fined, or how do we drive security as a first principle? And I think there's a couple things that we have to think about before we blindly go into that. And I think a lot of it is, we do point solutions for security, but it's really needs to be looked at from a system perspective and what the customer is actually going to care about. So something going into a Navy system that's going to last 30 years looks entirely different than something that's going into a very low cost, Raspberry Pi that's just going to play retro video games or something very simple. That looks different. Where something gets deployed looks different. So how you actually protect those systems, they could be completely different. They may utilize some of the same solutions, but you're really optimizing what that cost looks like for where it's being deployed. If I'm going to deploy something to a satellite in space, that looks way different than something that is going to be, a drone, that's flying around that could be, grabbed by an adversary and exploited. Very, very different attack surface for those. Or if I have a very low cost consumer device, they care about different things. So we need to make sure that we understand what a security solution offers to that end user and be able to communicate that effectively.
So tailored solutions, that's what you're saying. Tailor it to the need.
Yes, tailor it to the need, but in a more generic sense, it's really being able to communicate what a security solution in hardware actually means at a system level. If I implement a side channel protection, what does that mean when it's implemented in the system? It may mean a lot or it may mean nothing. It does depend on how it's being utilized.
Thanks, Chris. Aydin, you want to add anything quickly? We have a lot of questions actually, so
yeah, let's move on.
That's a great thing.
Let's move on to the next one.
Okay, Andrew, you want to go with the next
So this is, I actually want to know, what do you guys think, how quantum is going to impact AI hardware security? Like, is that going to be bringing new capabilities, or just, I guess, give me your thoughts on that.
I can take a stab at it. Maybe I think that quantum computing will affect cryptography, but I don't know how much it will affect AI security. Of course, AI security is a very big theme, but most people believe that quantum computer will be something that can accelerate anything, any problem you throw at it. But in reality, what happens is there is only a certain tiny, minuscule set of problems in the complexity theory where quantum computing can actually provide exponential gains. Well, those happen to be the problem that we build public key crypto systems, unfortunately. So that's the main concern, which is being addressed by NIST with their new quantum secure algorithms. So I do a lot of work in that as well. But in addition to that, I don't immediately see how quantum computing can impact AI in any kind of. But I think the vice versa can happen. I think these GPT or other AI tools can create quantum codes or quantum circuits that may be better than what we use today.
I'll just add on to that because I agree with a lot of what was just said. I think there's a couple of bottlenecks when it comes to AI implementing for security. And so a lot of the algorithms that we use now, neural nets, I mean, they've been around for decades, right? Those algorithms aren't really that much different now, but we're just now utilizing them for a couple of reasons. One is we have availability of data sets, and the other one is compute resources that we just weren't available back then. Quantum is going to increase those compute resources. But I think right now our bottleneck is probably, especially for AI security for hardware, is probably data sets. And I think that's kind of where our biggest bottleneck is. So even though we might have a lot more additional computing power that may enable some advances, but I think we're still going to hit a data set bottleneck that is not going to be advanced as quickly.
In fact, there's a question from Marita Dashgupta who mentioned that limitation in terms of AI model-based attack in academia is a lack of quality data set, even for generative AI models. So how do we stop overfitting our models on small data set, and how can we create more open source and standardized data sets? The standardization of data set is a big problem because I'm not aware of standard data set. We call them standard, but who is guaranteeing that the data in those data set are not tampered with or poisoned, or who is the authority of any data set, really, right?
Yeah, so I'll just jump in, sorry.
Go for it.
This goes into a software supply chain problem. It's very similar. We see a lot of software supply chain attacks currently, especially in open source software. Data set should be thought of the same way. It's supply chain problem. Where is your data sets coming from? Now, the problem in hardware is most of those data sets are proprietary. So you have to convince the Qualcomms, the Intels, the Apples, the ones who actually have a lot of data for hardware, to share it. Now there's models, there's federated learning models, so you can extract information and share it. But a lot of companies are seeing the value in their data. You see Twitter, you see Reddit, they've increased the cost of their API because of how valuable the data set sits on their platforms. So we need to figure out how to get data and how to convince those companies to actually share it and what that cost model looks like. I don't know if something can be done in maybe in the ME Commons with federated learning models to actually get all of those different hub members to share data through some sort of federated learning model. That would be great because you can start to actually generate data sets and generate those models while also protecting the data from those hub members. But there needs to be some community around it, and I just don't think we have that right now.
Yeah, so going back to like the ME Commons, I think that's one of the things that, as we're putting together the final request for proposals for this year, is making sure that we, the government, have access to the data sets and the models, because I think that's going to be critical to make sure that we're getting something out of ME Commons as a whole, but I think so that we can push the technology farther and make sure it's secure, right, from all aspects.
So, I mean, there's if you look in computer science, there's actually a lot of prior art in the sense that has been created for that, right? So, for instance, when you establish a connection to any web service, right? How do I know I'm connecting to CNN.com, right? So there are certificates that there are certificate authorities that exist, right? And we trust them in a daily basis, right? There's no reason why we can't create such an ecosystem for models and for data sets themselves, right? The second thing, things have to be repeatable. I work a lot in open source software. Nobody trusts your software unless they can rebuild it themselves, right? So even if you open source the data and saying, hey, here's all the data sets, and I didn't just use web crawlers, it's really from customer sites and blah, 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 who knows, right? But at the end of the day, if I can't repeat of how you created the model, even with some extra efforts, right? Either I trust you or I don't trust you, right? I have to be able to recreate how you achieved to come to the model. Otherwise, what use do I have knowing that you pretend you use that kind of data set, right? So this whole supply chain and the whole derivative of how you got from data to the ultimate model needs to be also supervised.
Yes, I agree. So yeah, we definitely need a standardization of this data sets and this ecosystem. One more question that came from Mark Johnson, and Mark is asking, are any of you involved in hardware design obfuscation to make reverse engineering of a schematic or layout difficult? If yes, what approaches have proved most effective? Or is this even done in real products? So hardware obfuscation is the question. How do you, any of you working in that domain, and how is that useful?
I did in the past. I worked in the context of logic blocking. I don't advise to new professors to work in logic blocking because it's very hard to find funding for these kinds of works due to various reasons. So yeah, that's my 2 cents on this. But I still think that there is some potential to advance these concepts, not through AI, but through a formal, rigorous study of logic blocking or other related solutions. Like we need to take take those experiences from cryptography. Cryptography is an old field. Modern cryptography is like 50, 60 years old. Hardware obfuscation, logic blocking, these are maybe 10 years old, maybe 15 years old. So if it will mature, it has to be through this rigorous analysis and more formal study of obfuscation problems.
So I did used to work in that space. I actually think obfuscation and logic blocking is a bad word nowadays, and you don't really want to use it. Logic redaction, I think, is the new accepted terminology, even though it's a slightly different approach. Now, to actually apply that to AI, I think we need to be careful when we talk about logic redaction because there are a lot of techniques out there. And what we try to do is we try to optimize the overhead of doing logic redaction to what we're optimize the overhead, the cost, and then the area and the power, and versus what we're getting security wise. And we have a hard time understanding what we're getting security wise. And we saw this with logic locking, where we had really great techniques, and then it was very quickly solved with SAT attacks and completely destroyed because we were thinking of them as cryptography algorithms, and we're using those same metrics, but they didn't make any sense. As we move to logic redaction, which is kind of the new accepted approach, where we're changing to a reconfigurable design, an eFPGA, or there's several other techniques, we need to be careful because how those are done and how those are implemented and how you optimize to make sure that you're getting the least amount of overhead for the performance is those optimization strategies are normally deterministic, which allows you to train models and then just undo the optimization and figure out exactly how the redaction was done and what the original design is. So that we need to be careful of because it's much different than cryptography. I think that's all I have to say on that.
Thanks. Andrew, you want to maybe take one of the questions from that has been asked from the audience?
Gonna turn off mute. We're probably gonna have to make this one short. Forgot to mute my phone.
So regarding the trade-off, right? That has a second time being asked, right? So we can actually verify this. So for instance, we do for instance EDA design over a large system, right? Where we're like tens of machines that we're running. You can see that an overhead is in the order of about 5%, right? And then comes the question, at scale, when you're running thousands of cores, 5% actually can eat into what the cost of your system effective means to you, right? And you have to literally at the end of the day balance against the risk. So if you lose your design for one of your core systems somewhere that somebody accidentally picked, or well, somebody picked up due to violations of security, right? You have to figure out how much is it worth to me to protect this, right? I mean, there's no simple answer of saying I can balance this in some way. It's always what is at risk.
Right.
So I think we're supposed to kind of conclude a little bit early. If you guys want to take like a minute or so and kind of give us a closing remark, maybe we'll go through the same order that we did the introductions. So I think, Chris, if you want to go give us your last thought.
All right, put me on the spot here. Okay, last thoughts for this whole area. You know, a lot of stuff in my current role, I'm less hardware focused. I'm more system focused. I'm looking at, you know, and I talked about this a little bit, is the implications. If I do something, what does that mean to somebody else? So, you know, a lot of times we talk about metrics, and a lot of stuff was optimization and how do you optimize or convince people to take the cost and you know, turn the dial up on security. But you know, if we had little knobs and it was the easiest thing where we could just say we'll spend a little bit more money and get a little bit more security, that security knob doesn't exist, and people have been working on that for decades. So, you know, when we're going through these processes and we're talking about AI and how we implement them, how we protect against them, always think about who this matters to, what specifically it's protecting against, and you know, what's the attack surface, and you know, what is you know, who is this useful for, and what does it cost? So if it's something that's a very point solution that's only for you know, a very small amount of chips because of the attack surface is impossible, or you know, if it can be done much quicker and easier through a software approach, so why would somebody attack the AI chip? Just think about those things before you go down that path, because the attack surface is very broad, and a lot of times we don't see a lot of the hardware attacks because it's much easier to attack specifically the software. So I think that's kind of my closing remarks, is always be thinking of the system and where things are implemented.
Great. I think, Hubertus, you're up next.
Well, let me conclude as like, what an exciting time to be a systems researcher, no matter where at the stack you are, whether you're at the hardware stack, you're at an operating system stack, you're machine learning, algorithms, distributed. I mean, it's all coming together in AI, right? No matter how you look at it, right? So very exciting. Echo the comments from Chris, right? You have to basically take in my opinion, a full stack view, right? You just can't look at a very tiny little piece and saying, well, you can't look at a very tiny piece and identify, hey, I'm going to make an improvement just here. You have to basically look at the implications of that particular part. And yeah, I mean, vote for me for president, I guess.
Aydin?
So
Last
my final thought is, first of all, I can vote for you, Hubertus. If you're running, let me know. My final thought is that this panel is not enough. It looks like there is so much excitement and enthusiasm into this topic that, you know, we need to probably have like a multiple day workshop in person somewhere nice, that we can all talk and figure out what are the key missing elements. And it looks like this is a problem that no one can alone solve. It should be a collaboration between academia, government, and industry, probably being led by government, if you ask my frank opinion, to standardize what we mean by AI security, to standardize new certification processes needed for AI hardware or for chiplets, to standardize these tests and figure out what needs to be done. And I look forward to, you know, talking to all of you, hopefully in the future events.
All right, Wayne, you got any concluding thoughts?
Yeah, no, I appreciate the conversation, and you know, I'd welcome feedback offline from, you know, anyone in the audience or even other panelists, as you know, we try to build ME Commons, because I think even in my area, I'd like to figure out how we, you know, start bringing, you know, even for myself, working more with the AI community, and probably reaching out to the technical execution area lead in that space, because I think, you know, in the months and the years to come, AI is going to touch everything, right? It's not gonna exist in a vacuum. So I think we need to start thinking about the holistic impact that it's going to have on our day-to-day lives and on our DoD systems. So yeah, thank you guys. Appreciate it.
Thank you, everyone. Thank you so much. So, Chris Sozio, I believe you're the last one, but not the
Yep.
least.
Yep, I'll end it hopefully short and sweet. One thing is I will say if government's at the lead, it might be a little bit of a slow process, as I'm sure a lot of us are aware of. But we take that with a badge of honor and would be happy to lead that. But I think this topic is going to be something, like I said previously in my opening statement, it is going to continue to be in our lives for, I mean, forever, really, in my opinion. We're going to have to constantly look at how to mitigate potential AI attacks or attacks on AI and hardware. And again, like what Hubertus and Chris said, is looking at the full stack and not just the hardware alone, trying to make sure that everything is secure and protecting our systems. I think that's about all I have.
Right. So thank you, panelists. That was an enlightening discussion.
Okay, so thank you, Chris and Prabuddha, for moderating such an exciting discussion, illuminating this discussion. I really enjoyed thoroughly. Hopefully, all the attendees, they also likewise enjoyed the discussion, and there are a lot of important takeaways from this panel. Of course, the really truly distinguished panelists shared their views, unique discussion points also came from the audience. So really appreciate the great effort here. I would like to thank Emily and Amanda from IEEE CEDA who helped us to organize this event. Thanks a lot for your wonderful support. I would like to thank the moderators, Prabuddha and Andrew. Of course, as I said, I really like the way you run the panel. So wonderful job. Thank you again. And finally, our appreciation and heartfelt thanks to all the panelists, distinguished panelists who attended the panel. I know they're extremely busy, all of you are, and thank you for sharing your valuable time with us. The summary of the discussion, as I take it, is that we should not stop the discussion. We should continue. Such an important topic. AI is going to touch us in many different ways, and of course, security of AI, both the hardware and the software, and also the data would be very, very important. So we should continue the discussion among us to come up with viable solutions, which basically means we need to have more events like this. Maybe as Aydin mentioned, maybe we should have a workshop, maybe a few days long workshop, and stay tuned for that. We'll definitely reach out to you for future events on this important topic. But in the meantime, I will encourage all of you to participate in the CAT for Assurance initiative and contribute to that. With that, again, thank you all. Have a nice Thanksgiving break coming up next week, and bye-bye.
Yeah,
Thank
bye.
you, everyone.
Thank you so much.
Thank you. See you.